webcast discusses Activity 2 of the lab, where we are exploring how unbalanced forces affect acceleration. And in Activity 2, there are two experiments. This webcast will talk about Experiment 1, where we examine how acceleration depends on net force. Okay, so here the independent variable will be the net force on the crate, measured in newtons, and the dependent variable will be acceleration, measured in meters per second squared. Okay, so we are going to fill out all of Table 1. So you're going to choose at least 10 values of net force, and we will record the acceleration for those values. Okay, so in the simulation, let's see, I've chosen 150 newtons of applied force, which gives me 33 newtons of net force. And I'm going to run the simulation for a couple of seconds so that I see the acceleration is 0.27 meters per second squared. And so I would put that in my table, and then I'm going to increase my force again, let's say to 200. And so now I've got 200 newtons of applied force. I'm going to record 112 as my sum of forces and my acceleration. And so I'll keep doing that until this table is filled in completely. Once I have Table 1, all of that data, now I'm going to use Microsoft Excel to make a graph of acceleration versus net force. Of course, the first step is to put my data into Excel, and so I've done that. Here is my data from Table 1, including the headers, in Excel, and now I'm going to just make a scatter plot of acceleration versus net force. So I'm going to choose those two columns and insert a scatter plot. And so here I've got my graph of the acceleration versus net force, and this is for a constant system mass. Okay, and be sure to put your axis labels, right? Net force here would be on the horizontal axis because that's our independent variable, and the acceleration would be on the vertical axis because that's the dependent variable. So I have this graph. I'm going to take a copy of it and I will paste that in at step 21 in the lab report. Okay, now that I have a nice linear graph, notice the shape of this, I want to fit a line to it so that I can write an equation that represents this data. And so I need to get a slope, and so I'm going to do linear regression. So I will go to the, let's see here, let me move that out of the way. I'll go to the Data tab, to Data Analysis, and I'm going to go down to choose regression. We're going to do regression on this data. First I input the Y data, which my y-axis is acceleration, so I'll highlight those cells. Then I'll input the X data, which is the net force. It's a good idea. I hope you will always do the residual plots and the line fit plots, because those are useful to see whether you got a good fit or not, and then say OK. It will bring you over here into a new tab, a new sheet in your work book. I like to, everything is squeezed in here, so before I'm going to go to Format and do Auto Fit Column Width, just to spread everything out a little bit so I can see it. And when I look at my line fit plot, the orange squares are totally covering up the original data. That means it's a very good fit. Look at my residuals, they're nice and random. My R squared is 0.9999. That's excellent. It's very close to 1. And so this is giving me a very good fit to my data. I've highlighted the y-intercept, and remember this x variable 1, that is the slope that we're looking for. Okay, so I'm going to take a picture of this and move it and put it in my lab report here at step 22. Notice the requirements here. It says to include the plot of the residuals and the line fit plot, highlight the slope of the fitted line. See, I did that. I highlighted it in yellow. Okay, so then, now that I have the slope, I'm going to write a physics equation to make a linear model that describes how acceleration depends on net force. Okay, and so I want to give good descriptive names for both of my variables. My independent variable net force, remember the symbol we use for that is sigma f. My dependent variable acceleration, we usually just call A. And so I've got my physics equation here. It is okay to ignore the y-intercept. It tells you that here because that is approximately 0. Then you want to explain the meaning of that slope, which is how acceleration changes as for every additional 1 Newton of net force. Okay, so we've got that. Step 25 asks us to simplify the units of the slope. And so our slope of this graph is meters per second squared over Newton. Remember that a Newton is a kilogram meter per second squared. And it tells us that up here. So now that I've done this, I can see that I've got meters per second squared in both the numerator and the denominator, so that can cancel, and I'm left with units of 1 over kilogram. Okay? It gives me this graph, which shows acceleration versus net force for different amounts of total system mass. And then there's also a table here. And so I'm going to put my own, I used a value of mass of 230. Yours may have been different. I hope it was. I'm putting the slope of my graph and then the inverse of the mass. Oh, my goodness. I don't have the right inverses here, but it would be 1 divided by 130. So whatever that is, you'll need to calculate it, okay? You would take the inverse of these things. 1 divided by 200 would be 0.005. Okay, so you'll fill out the rest of this table, and you'll see that the slopes of the graphs equal the inverses of the masses in every case. And so step 28 says, can we draw a conclusion about what that slope means? And yes, we can. Because in every one of these cases, in this table too, the acceleration or the slope of the graph of acceleration versus net force equaled the inverse of the mass. And so, and then also, when we simplified the units of the slope, they started out as meters per second squared over Newton, but they simplified to 1 over kilogram. Hey, that's the unit of an inverse of mass. And so because of these two things, we can say that the slope of acceleration versus net force means the inverse of mass. And so we can restate our physics equation by replacing the slope, the numerical slope, 0.005 or 0.004 or whatever you got, with the meaning, which is 1 over the mass. And so this equation is Newton's second law of motion.